Okay, this is discussion 1-1 for IB, and so this is going to focus on isotopes and also how to calculate average atomic mass. So first of all, when we think about atoms, imagine that if we have a chunk of copper, we cut it in half, we would have two chunks of copper, right? If we were to keep cutting it, we would eventually get to a point where we couldn't cut it down anymore and have it still be copper. Okay, this is assuming we have very, very fancy tools to cut this copper with. Okay, so eventually we would get to the smallest possible unit of a thing that we could call copper, and this would be an atom. So you probably remember from 8th grade that atoms aren't necessarily the smallest thing, right? We have subatomic particles, but atoms are the smallest unit of matter that still retain the properties of an element. Okay? Subatomic particles, then, are particles that exist within an atom, protons, neutrons, and electrons. But if I had a proton from a carbon atom and a proton from a hydrogen atom, I couldn't tell them apart. Okay? It's all the subatomic particles being put together that makes an atom. So when we talk about these subatomic particles, it's important to know their location, charge, and mass. So when we talk about protons, we abbreviate them with a P, very creative, I know. They're located in the nucleus. They have a positive charge and a mass of 1 atomic mass unit. Okay, that's sort of defined based on the mass of a proton. And you can remember that protons are positive because they both start with P. Neutrons are also located in the nucleus and have a neutral charge. They have the same mass as a proton, 1 atomic mass unit. Now electrons are located in the electron cloud and they're negatively charged. Now, they do have mass. But when we talk about their mass compared to protons and neutrons, we say that it is negligible. And that means that it's so small compared to the proton and the neutron that it really doesn't register. So I always tell people to imagine if you were to stand on a scale and take your weight, and then you caught a fly. Would the weight on the scale change? Probably not, unless it was some kind of horror movie fly, right? Because the mass of the fly compared to you is negligible. Okay, so do electrons have mass? Yes. Does it really even register next to the proton and the neutron? No. Now, you can find the atomic number on your periodic table. I want you to use the one on Google Classroom, okay? So I'm going to show you quickly on my periodic table. When we look at the periodic table, it has this handy little key right here at the top that always tells you where the atomic number is. Okay, so I've circled that for silicon. So when I look at hydrogen, for example, it has an atomic number of 1. So let's talk about what that means. That means that all hydrogen atoms and only hydrogen atoms have an atomic number of 1, which means they have 1 proton in their nucleus. So the number of protons in the nucleus is what determines an atom's atomic number. Okay? And that will never change for an atom. So if I told you that I had an atom of hydrogen with 2 protons, you would tell me that I was wrong. Alright, so pause for just a sec, look up your periodic table, make sure you understand how many protons are present in an atom of nitrogen. Okay, and so looking at your periodic table, you would see that its atomic number is 7, so the correct answer is 7. Alright, now let's talk about electrons. When we think about their charge, remember that electrons are negative. So in a neutral atom, neutral meaning having no charge, the number of protons have to be equal to the number of electrons. They balance each other out. However, it's really important to note that the number of electrons can change. You might remember that from 8th grade as an ion. Okay, we're going to discuss that later on, but it's important to know that for now, when we talk about neutral atoms, protons and electrons will be the same. But as we move forward and talk about ions, the number of electrons can increase or decrease. Okay, so the atomic number never changes, meaning that protons is always the same, and it's also equal to electrons in a neutral atom. Now, let's talk about neutrons, because neutrons are a little bit more complicated. We have something called isotopes. So an isotope is an atom with the same number of protons, but a different number of neutrons. And the number of neutrons in an atom can change. When it does, it forms a different isotope of that atom. So you can think of it as different versions of an atom with different numbers of neutrons. Now, we talked about how protons and neutrons have mass, right? So if the number of neutrons can change, then that means the mass of an atom can also change. To describe the mass of a specific atom, we use something called the mass number, and this is the sum of the protons and the neutrons. So if I wanted to know the mass number of an isotope of fluorine with 10 neutrons, I would need to look at my periodic table. Okay, so let's take a quick look at that. Now, fluorine on the periodic table is right here, and it has a mass number, there we go. It has a mass number of 9. Okay, so if I want to know the mass number of fluorine with with 10 neutrons, excuse me, the mass number is protons plus neutrons. Okay, based on my periodic table, I know that there are 9 protons in fluorine. Okay, the problem told me that there were 10 neutrons, so the mass number of this isotope must be 19. All right, so let's look at an example of 2 isotopes, chlorine-35 and chlorine-37. Now, that 35 and 37, those are the mass numbers. So this is one way to express the mass of an isotope. Write the name and followed by the mass number. They have the same number of protons and electrons. We know that the protons must be the same because chlorine always has 17 protons. That's its atomic number. And since these are both neutral, they have 17 electrons as well. What's different are the number of neutrons and the mass numbers. Okay? Looking at these, since chlorine-35 has a total of 35 protons plus neutrons, to get the neutrons, I would just subtract 35 minus 17. So chlorine-35 would have 18 neutrons, chlorine-37 would have 20. Now there is another way to communicate information about isotopes, and this is called isotope notation. Okay, so looking at copper-65, one way to write this is to write the name of the element followed by the mass number, so copper-65. Another way is to write the symbol for the element, so in this case Cu, put the mass number in the upper left-hand corner, and the atomic number in the lower left-hand corner. Now, we don't actually have to include the atomic number because we could easily look that up in the periodic table, but sometimes we do. If there were a charge, it would be in the upper right-hand corner. Since nothing's there, I know that this is a neutral atom. Okay, so the question is, how many protons, neutrons, and electrons are found in this neutral isotope of copper? So I want you to try this for a second. So pause the video, and then if you think you know the answer, go ahead and press play. Or if you just want to see it worked out, you can just let it keep playing. Okay, so this is my isotope, and I want to know the protons, neutrons, and electrons. Okay, now, the problem told me that the atomic number of copper was 29, which means there are 29 protons always and forever. Since this has no charge, there's also 29 electrons. Now, to get the neutrons, we have to remember that mass number is the number of protons plus the neutrons. The mass number is 65. I know that I have 29 protons because that's the atomic number of copper, so then I have to solve for the number of neutrons. So I find that there are 36. Okay, so let's compare carbon-12 to carbon-14. These are 2 isotopes of carbon. Now, in class, we dragged the dots to the different things, but we're not going to do that now, obviously. So let's just think about this. Protons and electrons have to be the same. Protons, because they're both carbon, and electrons, because they're both neutral. But since they have different mass numbers, they must also have different numbers of neutrons. Okay, so what I want you to do now is pause and try to fill out this table. Okay, so in some cases, the element is given, and in some cases it's not. So if it's not given, you have to use the other information to figure out what it is. Okay, so pause and then press play when you're ready to go over it. Okay, so boron. When we look at it on the periodic table, we see that it has an atomic number of 5, which also means, since this is neutral, that's the number of protons and electrons. Then, to get the neutrons, we would say, okay, I know the mass number is the sum of the protons plus the neutrons, so that means that 11 minus 5 is 6, so there are 6 neutrons. Now for the next one, I wasn't given the element, but I see that it has 9 protons, which also means the atomic number is 9, so it must be fluorine. That 9 is also the number of electrons. To get the mass number, I would take the sum of the protons and the neutrons. For the next one, bromine, I know that the atomic number is 35, so that's also the protons and electrons, and again, I would add together the protons and the neutrons to get the mass number. And finally, for the last one, I wasn't told the element, but I know it has 25 protons, which means the atomic number is 25, so it must be manganese, and that's also the number of electrons. To get the number of neutrons, I would take the mass number minus the number of protons. Okay, so let's talk about how isotopes are related to the average atomic mass of an element. Now, if you were to look at the periodic table, you might notice that the mass is in the upper left-hand corner. Okay? Now, we've been talking about mass numbers as whole numbers, but if you look here, almost nothing is a whole number. So titanium, 47.88, zinc, 65.69, sulfur, 32.06. I mean, obviously I could keep going. I won't. But we're not seeing a whole lot of whole numbers here. So the average atomic mass is what's on the periodic table, and this is a weighted average of isotopes based on their natural abundance. So that's just how much they occur in nature. So if we used a periodic table to look at the average atomic mass of neon, we would see in the upper left-hand corner here that it's 20.179. So there must be more than one isotope of neon. Now, here's why we need to calculate a weighted average mass. Imagine that we had a room with 100 people in it. 99 of those people weigh 170 pounds, and one person weighs 100 pounds. Is the average weight of people in that room 135 pounds? No, of course not, right? Because 100-pound people and 170-pound people are not equally abundant. So the average weight of those people would be really close to 170 because that's what most of them weigh, okay? So if you understand that, you understand the basic idea of a weighted average. Now, you might remember that chlorine had 2 common isotopes, 35 and 37. Chlorine 35 is most abundant, so why does the periodic table say 35.45? Well, because 35 is more abundant, it pulls the average mass closer to it. So the average atomic mass is always going to be closest to the most abundant isotope. Okay, so I'm going to give you an example using chlorine here, and we'll go ahead and do this on the document camera. And these are very rough percentages. I just want it to be nice and clean, so when you look at it later, you have a very clear-cut example. Okay, so we have 2 isotopes of chlorine, 35 and 37. Okay. We know the mass of chlorine 35 is approximately 35 atomic mass units, and for 37, it's 37. Okay. Now, the natural percentage abundance is approximately 75% for chlorine 35 and 25% for chlorine 37. So we're going to have 3 basic steps to calculate the average atomic mass. First, we're going to change the percentage abundance to a decimal. Okay, so in order to do that, we just take the decimal place and move it 2 places to the left. So I'd have 0.75 and 0.25. Okay, so far pretty easy. Next, I'm going to multiply the mass of each isotope by its abundance as a decimal. Okay, so I would take 35 times 0.75, and then I would take 37 times 0.25, and I would get 26.25 and 9.25. Okay, then finally I have to add the results. And when I do that, I get 35.5 atomic mass units. Now, this isn't exactly what's on the periodic table because I used pretty rough percentages, but it's pretty close, right? Now, when you look at your final answer, you can sort of apply some common sense tests to see if it makes sense, right? So the first thing that I would say is, okay, yes, it's a weighted average, but it's still an average. So my final answer still needs to be between those numbers, and it is. The second thing is, it should be closest to the most abundant isotope. So this answer should be closer to 35 than 37, and it is. Okay, so that's how I know my answer is correct, that it kind of passes those two common sense tests. Okay, so I want you to pause for a second and try to do this next problem, calculate this element's average atomic mass, and then I want you to look on the periodic table and see if you can figure out what it is. Okay, so take just a moment, pause and try this, and then when you're ready, you can press play and we will go over it. Okay, so these are our two isotopes and these are the percentages. So first, we have to convert our percentage to a decimal. So I get 0.198, 0.802. Next, I have to multiply the mass times the percent as a decimal for each one. And once I do that, I add my results, and I would get 10.81. Now, in order to figure out which element it is, I'd have to look on my periodic table. Okay, so I'm looking for something with a mass of 10.81. So upper left-hand corner, and I see that boron has a mass of 10.81, so this element must be boron. Yay! Okay, last piece of this is that so far we've used the abundance to find the average atomic mass, but realistically, the average atomic mass is given on the periodic table. So kind of a more interesting problem is to solve for the percentage abundance given that mass. So let's look at an example. Bromine has two major isotopes, 79 and 81. And we know that the average atomic mass is 79.90. So what is the abundance of each isotope? So we are going to use a system of equations to solve this problem. Okay? Now, I know you guys have been really missing systems of equations, so I'm really glad that I can make this happen for you. So let's walk through this on the document camera. Okay? Now, the nice thing about these problems is that once you practice a bunch of them, they follow a really consistent pattern, so you will get good at it pretty quickly. Okay, so we know the mass of each of the isotopes, and we know the average atomic mass. But the problem is we have two missing abundances, x and y. Okay? So let's let x equal the abundance of bromine 79, but let's go ahead and make that the abundance as a decimal. Since that's what we've actually used in our calculations so far, it's just going to save us a little bit of time. And let's let y equal the abundance of bromine 81 as a decimal. Now, the first thing we do is we always identify our variables, so we've done that. Now, we need two equations to write a system. So we have to think, what are two things I know about these variables? Now, if these are the only isotopes I have, their percentage abundances have to add to what? They have to add to 100, right? Because all bromine is one or the other. So their percents as a decimal then have to add to 1. So I could say x plus y equals 1. This is always your first equation. Okay? Now, the second thing that I know about these isotopes is I know their average atomic mass. So I need to write my second equation related to that average atomic mass. So I know that mass times percent as a decimal plus mass times percent as a decimal equals my average atomic mass. So let's try writing an equation for that. My first mass is 79, and its percent as a decimal is x. My second mass is 81, and its percent as a decimal is y. And that equals 79.90. Now, of course, we need to solve a system because this equation has two variables right now. We don't have enough information to solve that. So we're going to use substitution. So what I want to do is rearrange this first equation to isolate y. So I'm going to say y equals 1 minus x. Just subtract x from both sides. Then I can substitute this in for y right here. Now I would say 79x plus 81 times 1 minus x equals 79.90. Next, I distribute. Remember, the 81 is multiplied by the 1 and the negative x. Next, I collect my terms. And you don't have to show up every single one of these steps. Like you could have collected the 81 and the 79.90 in one step. I'm just trying to make sure that I break it down as much as possible for you. Okay, then I divide both sides by -2, and I get that x is 0.55. Okay, now, what does that mean? So x was our abundance of bromine 79 as a decimal. So what's the percentage of bromine 79? It's 55%. What's the percentage of bromine 81? Well, 1 minus 0.55 is 0.45, so it's 45%. Or you could just think of this as 100% minus 55 is 45. Okay? Now, again, you might look at this at first and be like, oh my gosh, this is a lot of work. Really, once you get to this point, it's just a one variable algebraic equation, okay? You just have to practice this enough that you feel comfortable setting up these equations. So what I would like you to do now is I would like you to try this problem, okay? So look at these two isotopes. The average atomic mass you can get off your periodic table, but to save you a little time, I will tell you that it's 121.75. Okay, so pause and then press play when you're ready to go through this, and we'll go through this again. Okay, so these are our two isotopes. I don't know their abundances, and I know that the average atomic mass is 121.75. Okay, so let's let x equal the abundance of 123 as a decimal, or sorry, 121 as a decimal, and y equal the abundance of 123 as a decimal. So our first equation, we know since those are our only two isotopes, that the total abundance has to add to 100%, so as a decimal, 1. So again, this is always our first equation. The second equation is based on this average atomic mass. So I have mass times percent as a decimal plus mass here times the percent as a decimal is 121.75. I rearrange this equation the same way I did before, and then I can substitute this in for y. Now I can distribute, collect my terms. And I get that x is equal to 0.625. Okay? So 0.625, what that means is that the percentage abundance of 121 is 62.5%. 100 minus that gives me 37.5% for the other isotope. Okay? So one thing you notice if you look at both of these, the process is really, oh, that's the other one, sorry. The process is really pretty identical, okay? You have the same first equation every time, and the second equation is always based on the calculation of average atomic mass. So for bromine and for antimony, okay? Again, you're just going to have to practice this. There's another video that specifically goes over this for you on YouTube. Okay, good luck. Email me if you want extra help, and we will find a time.